infinitesimal transformations, infinitesimal elements of the group. And we'll see that there's a lot of nice structure in this the infinitesimal transformations. Okay. So, but any questions before that? I mean, anything from the last time, or any other question you have? Yeah.
How we define that? What is the dimension of the group?
It's the number of parameters, number of continuous parameters. Yeah.
Okay.
Yeah.
Well, it can be say also the number of generators. It's different.
Which we'll see now when we discuss infinitesimal transformations.
Okay.
They'll be equal to the number of independent generators. Okay, so the idea, of course, we saw. So we are looking at the continuous groups, not discrete group. In the discrete group, there will be no notion of infinitesimal. Continuous groups. Okay. So in particular, in any group, we know there is a very special element, identity. Identity exists in every group, right? That's a very special element. So let's look at the identity and the neighborhood of identity. So, so you have the, let's take, some example. Let's say G, the U1. G was simply e to the I theta, right? When you think of the action on a complex plane. So the Z will be mapped to, G will map Z to Z times e to the I theta. No? So there's a rotation in the complex plane. Or you can think of the same as rotation in the real language. No? In the real language, it would be x, y goes to cosine theta minus sine theta, cosine theta, x, y. Right? So in these cases now, what is the identity? So in this way of writing it, identity is simply theta equal to 0, right? Because that is the 1. So z will go to z. Right? Or in this language again, you see it's theta equal to 0 because when theta is 0, these two vanish and cosine theta is 1. So this just becomes identity. So in both these ways of writing, what we see is that theta equal to 0 is the identity. Okay. So now if I start changing the theta a little bit, very, very small, if I turn on very, very small theta, it will be some group element which is very close to the identity, right? So the idea is to just think of turning on some small theta equal to epsilon. The reason why we write epsilon, because then the differential calculus, you have seen this limit, how you define the differentiation, right? So epsilon, in our, psychologically, we think of epsilon as very small. So that's the only reason why I'm writing like that. Right? Otherwise, you could have just written as theta and just say it's small. So if you write it like that, then this G is e to the I epsilon, and I make an expansion. Since epsilon is small, I can make a series expansion in powers of epsilon. Of course, the first term is identity, 1, and then the next one is I epsilon, and so on, and higher orders in epsilon. Epsilon square and higher, right? But when we talk about infinitesimal, the idea is to ignore all these higher order terms and just focus on the linear terms. First one, so epsilon is very small. So basically what you do, so you're just picking out, so this is the same as Taylor expansion, right? We're just making a Taylor expansion. So we have G, which is a function of epsilon or theta. So what we are doing is we're just making an expansion. G of theta, for example, is G of 0 plus theta times dg by d theta evaluated at 0, theta equal to 0, and higher order terms. So what we are looking at is the first derivatives of the G at identity. So the picture would be something like, so there's some group here, and I'm just drawing the space, the group as a space. Like we saw for SU2, the group was a group manifold was a 3-dimensional sphere, right? We will discuss that again in more detail later. But and say in this space, there is some particular element, the special element, which is identity. Okay. So what we are doing is just looking at some small neighborhood and studying this. These are the infinitesimal transformations. So that's, and these are called the generators of infinitesimal transformations, the generators of the group. These are called that. So, of course, in these two examples, there was only one parameter. So then you can only differentiate with respect to that one parameter. So there's only one generator, right? But imagine that you have some group which has many different independent parameters, right? Then with respect to each of those, say theta 1, theta 2, theta 3, etc., then with respect to each of those parameters, you can differentiate, right? And then evaluate that at the origin, at the identity. So then you will get different generators, right? So the number of independent generators will be equal to the number of the dimension of the group, which means the number of independent parameters that you require.
You said that the new elements which we created by using epsilon is really close to the identity element. So is there any distance notion between group elements?
You can define the metric also. Yeah, sure. You can define a metric. Perhaps that we'll discuss much later, because I mean that we will describe something called what is called killing form. Okay? But that we'll discuss much later.
But we can imagine that like a manifold where 1 and epsilon elements are really close together.
Yeah, 1 and 1 plus epsilon, let's say. Yeah, they are very close. Yeah. Yeah, you can introduce all this notion of topology and so on in the spaces. These are smooth manifolds. I mean, at least in the examples that we are discussing. Here is a circle. This is just a circle. Theta going from 0 to 2 pi. This is a smooth manifold.
I believe that formally speaking, we have a smooth manifold, and we are now, since we are working locally, we work in a batch. So in some sense, we have the notion of the distance from Rn.
That's right.
Because we are working in just
exactly.
A batch or an open neighborhood.
Yeah, actually this is just a tangent space. What we're doing is just a tangent space. So, I mean, if you look at, this is a circle, okay, and let's say theta equal to 0 is this point, right? And so, when I look at a small variation, this is like a tangent to this point, right? So, what this Lie algebra, this is called the algebra, Lie algebra, it's called Lie algebra. The Lie algebra is really, should be thought of as a vector space, right? Because you can add, no, I mean, you can add, you know, you can think of g like n times that, or any x times that you can define, right? Because you can talk about again g is equal to e to the power of I x times epsilon, no? And take the expand it with respect to epsilon, you'll get x times I, no? So you can multiply it by numbers, real or complex depending on the kind of group. In this case, real, right? Because theta is real.
So in some sense, the Lie algebra is a tangent space to the Lie group at the identity.
Exactly. I mean, so far I have not talked about algebra yet. Huh?
But you said this is the Lie algebra.
It's called Lie algebra, but I have not talked about the algebra yet. I mean, so far from this discussion, what you see is a vector space.
Okay.
So far. Then there will be another structure on it. That is what makes it very interesting. It's not just a vector space, but it's a vector space with some additional structure, some extra structure. Huh? And that will be the crucial part. Yeah. So this is basically the notion. So in this case, you see, in this way of writing it, when I take the derivative with respect to theta, I will just get I. So the generator is just I, right? The generator in this case, the generator. This is this is what we is a name definition. Generator for this example is simply I. When you think of U1 like that, or if you think of in this language, suppose you think in terms of this language, let's again expand this to the first order in theta, near theta equal to 0. So what will I get? So if I think of expanding, so this was the idea, and that we're thinking about. If I write it like this, cosine theta minus sine theta, and cosine theta, and now expand near theta equal to 0. Now theta equal to 0, of course, is identity. So the first term is identity. Okay. Then I look at the first order in theta. But the expansion of cosine theta starts with the theta square. So that's irrelevant. Right? But sine theta starts with theta. Okay? So you will get here, so plus theta times 0 minus 1, 1, 0. So when I take the derivative with respect to theta at theta equal to 0, this will go away and you just end up with that. So the generator is that one, 0 minus 1 times. So you call this a generator, and then the infinitesimal transformation is simply, I mean, this, as I said, this is a vector space, so you can just multiply by any number. This is like the this is like the basis of the vector space, and you can multiply by any number and add, subtract, all that. Okay, so just as a curiosity, you can see that the square of this is 1, minus 1, and the square of this is also minus identity. Okay, that's just a curiosity. Nothing.
In fact, I have just checked this.
Yeah. Yeah. Right. Okay. So this is, we'll see later on. I mean, okay, these groups are very simple. As I said, these are just one-dimensional groups, right? So there's only one generator, and there's no additional, no extra structure. So they're very simple ones. But in the more complicated cases, like non-abelian groups, this is an abelian group. Non-abelian groups, this will be absolutely the crucial. You study the Lie algebra, the properties of the Lie algebra I have not introduced yet because there's no algebra here. This is abelian, that's why there's no algebra. But once you have a non-abelian group, there will be a very rich structure in this vector space. You can put an extra structure. And study of that is what, you can really learn a lot, essentially. For this course, we'll be only focusing on that, not the group manifold part. We'll be just studying the neighborhood of the identity. And it will have basically all the information which you need to construct the representations and everything, essentially. Okay. But before going to that, let's just see how, how this, all these symmetries and this notion of the generator plays an important role in physics. So just this I think somebody mentioned last time. This just Noether theorem. So you mentioned that, right? So indeed, you all have seen Noether theorem, right? So let me just put it to remind you again. So imagine that I'm just looking at some classical system, right? Classical system with some number of variables, Qi. Okay, Qi are some variables. You can think of as say so several particles moving in one direction, and the different particles are labeled by I. Or you might imagine there's just one particle which is moving in so many dimensions. Dimensions are labeled by I, or in any case. So these are some variables. Okay, some variables. That's your basic variables. And then, so Qi are the what we call configuration variables. And in the classical mechanics, you know that one way to think about classical mechanics is in the language of Lagrangians, right? Lagrangian and the action and so on and so forth. Right? So the Lagrangian is simply d by dt, the integral dt of some Lagrangian density, right? Lagrangian density will depend on all these Qi's and their dots and the time derivatives. Right? By dot I mean these are all functions of t, right? Time. And dot, it means derivative with respect to t. So q dot is the shorthand notation for dq by dt. Okay. So it's going to be some function. And this will be the Lagrangian density, and then of course you can, using the Lagrangian density, get the equations of motion, etc. Or if you wish, you can go to the Hamiltonian canonical formulation, go to the Hamiltonian. So there are various, but this is our starting point. Okay. Now suppose that this action has some symmetries. Okay. And those symmetries I label, those symmetries are going to act on the Q's, right? So let's suppose the symmetry is Qi, goes to some Q prime, some, let's say, Fi, which depend on all the Q's, as well as some parameters, let's say Sa, some parameters. Okay? So this is continuous transformation. We talk about continuous transformations which depend on some parameter SA. Okay? Like here theta or, so, but now I'm considering the very general case. So let's suppose, and what we are saying is that these transformations are such that this is invariant. Lagrangian is invariant. Okay? So that's why we call it symmetry. Symmetry means a Lagrangian is invariant, right? Okay. So these are some transformations which leave the Lagrangian invariant. And we will consider at the moment, this is some terminology which I noticed that it's used in the notes. It's called global symmetry. Okay, that is because there is a concept of also local symmetry, but I don't think you have seen that so far. I mean, I think you will see it when you discuss QED, for example, or even particle physics course. You will see that the local transformation versus global transformation. But in this particular case, what we mean is that SA is not a function of time. Okay? See here, everything is a function of time, right? But these SAs are not functions of time. Okay? But there are even more general situations where you can allow the SA to be functions of time. Okay? Those are called local transformations, which means over each time you can decide to transform in different ways at each time. No? But we are not considering that. So that's why it's called global. It does not depend on t. Right? For all t is the same transformation. So anyway, so if you have global transformations, global symmetries, then what does it mean? So that means Lagrangian is invariant in symmetry. So okay, and let me also define. I have to also tell you what is the identity, right? So identity, I will take it to be the point where all the SAs are 0. That's up to you. I mean, you can choose your parameters S in such a way that SA equal to 0 means no transformation. Qi goes to Qi. So we will set the notation that when all SA are equal to 0, then this is an identity transformation. Okay. Which means Fi of Q and SA equal to 0, or the SA equal to 0, is nothing else but the Qi itself. No? So no transformation, Qi goes to Qi. So identity is labeled by this. We have chosen the origin in such a way that SA equal to 0 is identity. Okay. Now, so let's see, let's look at, so what does it mean, as we said? So we have L, now I evaluate L on these guys, Fi, Q, QT, SA do not depend on T, and Fi dot, QT, SA. Lagrangian depends on that. I mean, this is how it would be after the transformation. But we are saying that it's a symmetry of the theory, so therefore this is the same as the original Lagrangian. Qi dot. Okay. So which is the same statement that when I make this transformation, Lagrangian does not depend on this parameters SA. That's why it's a symmetry. Right? But if so, what I can do is I can take the derivative with respect to SA on both sides. Left hand side clearly does not depend on SA, so that is 0. Okay. So we conclude that this implies that if I take the derivative dl over dsa for each a and evaluate that in particular, I mean it should be 0 for any value, but let us evaluate at sa equal to 0.
Should this be a partial derivative? Because there could be
partial derivative. Right, partial derivative, exactly. Yeah. Because there are several parameters, correct. Okay. So this should be true for each SA. This should be equal to 0. I mean, it's like an empty statement, right? It looks obvious. But let's see what does it mean. Let's just try to evaluate that explicitly. Let's just take the derivative explicitly. And maybe I can do it here. So one has to just apply the chain rule. I mean, the only way the SA enters here is through Fi and Fi dot. So just use the chain rule for taking the derivatives, right? So d by dsa of L that L is equal to dl over dfi times dfi over dsa. Everything to be evaluated at s equal to 0. Okay. Plus dfi dot over dsa. Okay. And then okay. And then dl by df. That is what at this stage we have done. Okay. Now, but again, you see, I mean, if I look at the fi depends on q, the q depends on t, and s. Right? S does not depend on t. So when I take the, what does it mean fi dot? Fi dot is simply q dot. Okay. So what is fi dot? Fi dot will be taking time derivative. This will be df by dq and q dot. Right? Let's say take all the sum of j. That's what it will be. Right? Okay. So maybe I don't even have to do that actually. It's even simpler. It's even simpler, yeah. So okay, just leave it as it is. I don't even need to do that. So this is the same as, of course, d by dsa of df I by dt. Fi dot is simply that. So this is acting there. This is not acting there. Right? Okay. So now let's take. What we can do is, I mean, you can compute d by dt and d by dsa. Right? So this is the same as dfi by dsa and d by dt. This object. And now let us rewrite this whole thing. This whole thing is multiplying dl by dfi dot. Okay. So far. Now let's rewrite this whole thing as a d by dt acting on the whole thing minus d by dt acting on that. Okay. That I can do. So this expression I can write it as d by dt of dfi by dsa and dl by dfi dot. Okay. Derivative minus, I have to subtract now where the derivative is there. So minus df by dsa and dl by dfi dot times d by dt. I mean, and d by dt acting on that. Of course, I still have that term, right? So this term also, so there is a I here. If you look at this term now, the first term, I mean, this so far I'm just manipulating the second term here. This whole thing is second term, but I still have to add this piece. But that piece is, you see, again, it's a dfi by dsa, and there's a, so taking into account the minus sign, that is simply minus dl by dfi. Okay. So this whole thing, the whole variation is that. Now, and this we have to evaluate at s equal to 0. Okay. But at s equal to 0, so I now evaluate this whole thing at s equal to 0. And because it becomes simpler. So if I evaluate this at s equal to 0, this term, after all at s equal to 0, f is the same as q. Right? So this is nothing else but dl by dq dot. So this I have to evaluate this at s equal to 0. All the s is equal to 0. But when all the s is equal to 0, L which was a function of, remember, f which is q depends on q and s, and f dot which depends on q and s. But if all the s is equal to 0, this has nothing else but q and q dot. Okay? So this simply becomes d by dqi at s equal to 0, and this will become dl by dqi dot. But this is the equation of motion, right? I mean, from the original Lagrangian, if you take the derived equation of motion, this will be exactly the equation of motion. So on the equations of motion, this will be 0. Right? So those configurations will satisfy the classical equations of motion. This will be 0. And then what you're left with is that. That's the only thing that's left over. But we know the whole answer is 0. So therefore, this will be 0. But this gives you a very important quantity. Because what you're saying is that on the classic, when the equations of motion are satisfied, because that I'm assuming, otherwise I cannot set this to 0. Right? So if the equations of motion are satisfied, then this object is independent of t, which means it's conserved.
Constant of motion.
Constant of motion. It's conserved, right? So now this quantity, so what is this quantity? Now we are evaluating at s equal to 0. We are evaluating what this implies s equal to 0. So here I put s equal to 0. And when I take s equal to 0 here, this is nothing else but qi dot. So this is exactly the generator, you see. Because that's what we said, right? We take the first derivative, I mean f or the transformation. The q went to f of q. Yes. But then s equal to 0 is identity. So now when we take the first derivative, it is exactly the infinitesimal transformation. Okay? So what we are saying is that if you apply the generator, I mean this is the generator, okay? I mean as many generators as the a's, okay, as essays, as a number of essays. And for each of these generator, I will get a conserved quantity. So this is that, yes. So maybe we should just, okay, let's consider some simple examples to get this straight. In fact, the examples will be exactly based on the rotation group.
But for this example, we were free to choose any function f. So
no, but it should be a symmetry of action.
yeah, if we can find that something satisfies this form,
Satisfies that the Lagrangian is invariant.
but what kind of functions fi that we can choose?
That depends on the Lagrangian. You see, I mean, in general, if you take a generic Lagrangian, it will have no symmetries, right? So symmetries will be when there are some space. So let's take an example, right? So let's take the simple a free particle moving in 2 dimensions, right? Let's say a free particle is moving. This Lagrangian is simply half m x dot square plus y dot square, or let me call x1 dot square plus x2 dot square. So this is the free particle, a free particle moving in 2 dimensions in a plane, on a plane. Now this Lagrangian has some several symmetries. Of course, there's a translational symmetry. So you can take x1, x2 and shift it by any amount, x1 plus a, x2 plus b. Right? Doesn't do anything. Where the shift, these are time independent. Like I mentioned that s's do not depend on t. Right? So these are like s's. So these are so these do not depend on t. If they don't depend on t, of course they don't appear here, right? Dot will remove that, right? Time derivative. So this is clearly a symmetry, right? But there is also more symmetry. I mean, if I apply, this is a rotational symmetry, clearly, right? x1 dot square plus x2 dot square. So if I take x1, x2 and rotate it, cos theta minus sin theta, cos theta, x1, x2, where again theta does not depend on t. Right? These are the parameters. This is a parameter. It does not depend on t. You plug it there, and you will see that right? So these are clearly the symmetries of this theory, continuous symmetries. Apart from that, of course, there's a parity transformation. You can reflect x into minus x. But here you are talking about. You see, these conserved quantities are only for the this continuous transformations. Because here we take these parameters, s's, no? So the continuous transformations. So these are the symmetries that we have. So a three parameter family of symmetry, right? In this case. Now that will not be always generally case. Suppose, for example, instead of considering this, I consider a 2-dimensional harmonic oscillator. In this case, I will have some omega, some constant, omega square, let's say, x1 square plus x2 square. Right? In this case, this symmetry is still there, but not that. Right? So it depends on the details of your, the Lagrangian. Generically, Lagrangian may not have no symmetry at all. For example, you may have a term, I don't know, some alpha times x1, x2. In this case, not even rotational symmetry will be there. Right? So in generic case, there will be no symmetry. But in special cases, there will be symmetries. Fortunately, at least in the fundamental theories of physics, there are a lot of symmetries. There are a lot of symmetries. That is quite a remarkable feature. Okay, so let's go back to this case where you have the largest symmetry that you have.
Are you sure that this is the largest or?
Continuous symmetries?
Maybe, yeah.
Continuous symmetry, yeah. You can have discrete symmetries, of course, yeah.
Yes, but I mean, we just guessed what kind of transformations might leave that square form invariant, but there might be another one that we couldn't think of. I'm sure that
I think this is all. Because this is the symmetry of the plane, a metric of the plane, flat metric on the plane. Euclidean, this Euclidean symmetry. I think that's all. I think so.
Yeah,
sometimes it's hidden. Yeah, I agree.
Yeah. If somebody comes in and says that there is another symmetry hidden when you make that transformation, so that is a possibility.
Oh, sure. Yeah. Whatever symmetries you can find, continuous symmetries you can find, for each of them there will be.
So there is no theorem against.
That theorem is this theorem, the Noether theorem. For every independent symmetry transformations, these SAs are the independent parameters. No? For each of them, I get one conserved quantity.
For example, a rotational symmetry will be.
That will not be continuous, right? They're discrete.
But if we choose to use complex numbers to reflect things, we can make it continuous, and then we can.
How? I mean, if you write this as a complex, it will be.
For in front of cosine, we can put e to the I phi, and for phi equals pi, it is like reflection.
Yeah, but it's not because you have to make sure that throughout it makes sense, no? I mean, if I multiply by e to the I phi. It should make sense for any phi. Otherwise, it's not. I mean,
doesn't it?
No, because these are real. It's complex.
X must be. That's right.
So yeah, I mean, so that will be discrete because that will be only valid for phi equal to pi. No. It should be something that you can continuously change the parameter. No? And for all these values, it should make sense. The transformation should make sense. Okay, so given this, so let's look at, for example, this transformation. So the parameter is theta here. So S is theta, and you see what it's doing. So if I look at so F1, I mean remember this Fi, the transformation was Qi went to Fi, which was a function of Q's and S's. So for us, instead of Q, I'm using x1 and x2. Okay, and F1 will be, so what does it mean here? F1 is nothing else but cosine theta x1 minus sine theta x2, and F2 is sine theta x1 plus cosine theta x2. And now I just look at the theta equal to 0 indeed corresponds to the identity, like here, S equal to 0 was identity, here theta is equal to 0 is identity, and I expand around S equal to, theta equal to 0. So this will be, so what it is going to be, so F, so let me just erase this part, go over here. So this is, in the small, for small theta, this guy is simply x1 minus theta x2, okay, first order in theta. So this is small theta, and this guy is theta x1 plus x2. So the first, I mean, the derivative, taking derivative. So if I look at this quantity here, so what it is saying, d f1 over d theta, s is theta, it's only one parameter here, s equal to theta, you get minus x2. Okay, so that term inside is minus, inside the d by dt is minus x2 times dl by dx1 dot. Okay? And then I look at the f2, which is x2 here. So that is theta x1. So first derivative will give me plus x1 and dl by dx2 dot. Right? So that formula says that this quantity is conserved. D by dt of this is 0. Right? But what is dl by dx1 dot? It is simply mx1 dot. So you find here this quantity is minus m. Let's see. So my m times minus x2 x1 dot, and then plus x1 x2 dot. But that's just the angular momentum. I mean, this is momentum. M times x1 dot is p1. So this is x2 p1, or minus x2 p1 plus x1 p2. This is just the angular momentum. Right? In two dimension, there's only one component of the angular momentum, the z component. So that's that. So this, you see, the rotational symmetry. This was just rotational symmetry, and the rotational symmetry implies conservation of angular momentum. So this is quite important. I mean, so how in physics the symmetries play a role in giving really a conserved quantities is very quite a deep result. No? What about these symmetries? See, if I look at that, these are two independent. A and B I can independently vary, right? So first of all, let's take B equal to 0, and I just look at the variation with respect to A, right? But that means only the df1
Momentum only?
huh?
It will imply
Exactly.
because this would be 1 and we will have the partial L by partial figure, which is the generalized moment.
Exactly. For each of these, because you can put the no translation here, only the translation there, right? In that case, you will find just the only the f1 d by df1 will be non-zero. It will be 1, and then you get dl by dx1 dot, right? Which is just x1 dot. Is that clear? I mean, what I'm saying is that this one. So if I look at this parameter, look at the variation with respect to a parameter. In that case, only df1 over dA. Only this guy contributes, right? Because A does not enter here. So only the first one. And that's going to, this is going to be equal to 1 from here. This is 1. And then this is multiplying dl by dx1 dot. Q1 is the same as x1. T by dx1 dot is simply mx1 dot. So this guy is mx1 dot. And this is conserved, so that's the first momentum along the first direction. And the same thing will happen if they take derivative with respect to B. You will get momentum along the second direction. So that is the consequence. This Euclidean symmetries here, the translation together with the angular rotation, and they correspond to the linear momentum, conservation of linear momentum, and conservation of angular momentum. So this is the very general result. Okay, and the same thing will happen. I mean, now if you look at, okay, this was an simple example where I just considered in 2 dimension. What if I had considered 3 dimension? In 3 dimension plus x3 dot square. So this is now a 3D. In that case, we'll have a more general symmetry, rotational symmetry in the 3 dimension. Okay, and they will depend on 3 parameters because there are 3 Euler angles, right? 3 Euler angles, and then when you take a derivative with respect to each of these Euler angles, you will obtain exactly the same way as we did for 2 dimension. You will get the 3-dimensional angular momentum conservation. So all the 3 components of angular momentum, right? So you'll have a xi pj epsilon ijk. Okay. ijk. So for each I, you will have one angular momentum, different directions of the angular momentum, and they will be conserved.
When we write it in that form, is there a sum that is implied? Or
Yeah. Oh, I should mention this. We always take it for granted. Wherever there is a, this I should define once and for all. Wherever there is a repeated sum, a repeated index, it means that sum is implicitly assumed. Now, good point. I mean, I should have mentioned that. Because we are so much used to using this language that I forget to even mention that. So really this means summed over I. Huh? Here also summed over I. Everywhere where you see repeated index, right? The sum is understood. If there will be situations where even with a repeated index, sum is we don't mean sum. In those cases, I will say explicitly that here there is no sum. Okay. But whenever I don't say anything, that means it's a sum.
Because in the translational case, you can put a parameter, for example, only for one component.
Yeah, precisely.
But in the rotational case, we can't do it. That's why we need to add.
No, I mean here you see the A is a free index. Here, SA, I is summed over.
Yeah, but for some transformations, putting some theta or SA makes at least two functions change, not like in the translational case. So
Right.
we need to know which derivatives that we add.
Precisely, that is what happened here for the rotation, right? Because both the F1 changed and F2 changed,
Yes.
right? So we needed to take two terms. That is why we got this
The total
expression.
of two terms are conserved, not each term.
Not each term, no. Yeah, here, because here the sum is there. This sum, the A is a free index, but I, this is repeated, so here is a summation over I. Yeah, correct. Yeah, this is crucial. I mean, that point I forgot to mention.
Yeah, but when we have this, two parameters like A, B,
Yeah.
should be a sum over.
No, for each, I mean, I can take derivative with respect to each of the parameter, right? All this I'm taking derivative with respect to just one parameter. Pick any one,
I see.
right? And this should be true for any choice, no? So here I have three parameters, A, B, and theta, right? Call this S1, S2, and S3, no?
Okay, so in the case of momentum, it should be conserved in each dimension, for each dimension.
Each direction, yeah.
Each direction.
Yeah. So, I mean, that is assuming that I have the symmetry. You see, that symmetry may not be there, no? I mean, it is just because I considered a flat, you create a plane, flat plane, and I consider a particle moving in that. That's why, I mean, on a two plane, right? That is why you had this, right? If the plane was not flat, some curved plane, that symmetry will not be there, right? So it depends. I mean, so this was a very simple example, no? The flat plane. Right. I mean, so whatever give me the action and find the most general transformation symmetries that we can find, and they will be continuous symmetries, and they'll be parameterized by a certain number of parameters, okay? Independent parameters. And for each of those independent parameters, there will be a conserved quantity. Okay. Okay, so I think, yeah, that is about it for the Lie algebra. We'll come back to the Lie algebra. I mean, this was, as I said, a very simple Lie algebra, very simple generator because abelian. So now we go to the the simplest non-abelian group, which is the SU2 or SO3. So we will discuss now that. But before I move there, any further questions on this? Because then I have to clean up all the blackboard. Yeah.
There, we say that the symmetries has to be the most general ones, right?
No, I mean, if you take a Lagrangian, then you ask the question, what are the symmetries of the Lagrangian? Okay? And find all the possible symmetries of the Lagrangian. Right? Even if you find only one symmetry, you find one conserved quantity, right? But you're obviously interested in finding out the maximum number of conserved quantities, right? Because that makes your job easier. Because when you want to solve the equations of motion, sometimes the equations are very difficult to solve, right? But if you know that these quantities are conserved, some things that are going to be fixed. It helps you to solve the problems. Or, yeah.
For example, we we can change scale for x. Scaling for it, lambda times x.
No, that is not invariant. That's not invariant. That would be some kind of conformal symmetries. I mean, that not this particular model. Yes. But there are very important theories which you will study, but in quantum field theory context, gauge theories, electromagnetism, Maxwell's theory, four-dimensional. Four, of course, is defined in four-dimensional. Four meaning 3 space and 1 time, Minkowski space-time. That is conformal invariant. So those things have important consequences. Conformal invariant classical. That's another thing I should mention. All this discussion is purely the classical level. Many times it happens, not many times, but sometimes it happens that certain classical symmetries are broken at the quantum level. Okay. This happens, and there are important consequences of that. But this discussion is purely classical.
Is there a generalization when we have non-continuous transformations, or if there will be any conserved quantity for non-continuous?
No, not conserved quantities, no. I mean, you can define R parity charge and so on, but that is not as powerful. I mean, these quantities are really, of course, for everything there will be some, some conserved quantities in the sense of some charge, R symmetry charge or something like that. No? Some parity, etc. You can talk about it, but these are very powerful. There nothing changed. I mean, you talk about some discrete charge. Let's say something is even or odd under Z2. Let's say. So you started with some state which has Z2 even. Finally, after all the evolution, the final state will again have that Z2 even or odd. But these are like continuous. I mean, even the momenta can be continuous, right? I mean, not just these parameters are continuous, but the quantity which is conserved, the momentum or the angular momentum, classically, they can be any continuous values. So, so describing, I mean, this is quite much more non-trivial somehow.
Is there any converse to the Noether theorem? Because we are interested in constant of motions or conserved quantities, and the aim is to produce such quantities using the symmetries of the Lagrangian. But it could be, in principle, the case that there are constant of motion which don't arise from symmetries.
Yeah,
we don't want to omit those. So, are we sure that every constant of motion arises from a symmetry, or it could be the case? Even if partial converse or a counter example for this?
I mean, I would find it very hard to imagine that, to have it, the accidental conserved. Basically, you are saying, is it possible that it accidentally happens, right?
Yeah, if there is a conserved quantity which doesn't arise from any symmetry.
That would be very surprising. Okay, I don't know. I'm not sure. It would be very surprising to find. Maybe you can try to work backwards and if you have a conserved quantity, try to work backwards and guess what. Because sometimes symmetries are not manifest, no? Here the symmetries are very manifest. But as you are pointing out, sometimes it can be quite complicated. For some interacting, with some potential, there may be some hidden symmetry, which may not be visible so easily. But in those cases also, it will be very difficult to, the equations of motion are very difficult to solve, right? I don't know.
For example, I'm not sure if it is conserved, but in classical mechanics there is also a quantity which is R cross L or something like that.
Angular momentum.
L is angular momentum. What else?
R cross L or L cross R or something like that. It is symbolized with A or something. I don't know the name for it, but
what is L? Is a continuous symmetry?
Is a conserved quantity during the motion. Anyone knows? I don't know. Maybe
classical mechanics?
Yes. It's symbolized with vector A, the capital A.
What is capital A?
I don't know the name.
Is it electromagnetism or
No, in classical dynamics, you
Uh-huh.
can construct such a vector which is conserved during motion. It's like something Runge-Lenz vector or something like that.
Laplace Runge,
Can be, yeah.
I think this.
It's another
It
quantity.
is, yeah. It's regarding. I think it relates to the energy. I think.
energy conservation? The conservation of energy.
Maybe. I think it is called the Laplace Runge vector.
Okay.
R cross L or something like
It is
that.
regarding if we have for example, the sun and the moon, and maybe the moon is not in the same precision of the moon. It tries to measure this, so I can remember something about it.
Yeah, Laplace Runge-Lenz vector.
Yes.
Something like that.
L is what? Angular momentum?
Yes.
Angular momentum.
You
R
cross
cross
it
with R.
again. Yeah,
Okay.
again with that.
Yeah, I don't know. Is there any symmetry?
Essentially, the idea about this is that, for example, when we are dealing with harmonic oscillator in quantum mechanics, we can talk about the ladder method, the creation and the annihilation operators.
Right.
And I was asking, in hydrogen atom, we don't do that. There is no method like the ladder one for harmonic oscillator. And I was told that using this kind of vector, we can treat the hydrogen atom also by raising and lowering, but using this kind of
Yeah, I think there was a, because you see, I mean, this issue of there is of course a question of degeneracy, right? So, I mean, from the angular momentum conservation, we know that it doesn't matter which angular quantum number is. I mean, for a fixed total angular momentum, all the other quantum numbers, which direction the angular momentum is pointing, does not matter. No, it will have some degeneracy. But then there was this radial quantum numbers. And why, why those, there was an issue why I forgot now, why because total energy depended only on the n. There were three quantum numbers, L, M, and N, right? L was the total angular momentum, M was the J3 quantum number, and N was another quantum number, right? Yeah, the issue was why, normally you would imagine the angular momentum also contributes to the energy, right? So total energy must be also dependent on L. But the point was that L is independent of L, depends only. So I think there was some other symmetry. No, I don't remember, some SO4 symmetry, something like that was there. You could understand that in terms of some symmetry, but I don't remember now. Yeah, so that was again, that's one of those hidden symmetries, was not immediately visible. Okay, so any other comment, questions?
So in that case, the Lagrangian would be very different, right? If we have other symmetry, so the Lagrangian would be not this, but additional kind of.
Yeah. That's right. I mean, in general, rotational symmetry can be is more common if there's some radial interaction which depends only on the distance between the particles. So then there could be a radial potential. Any potential energy which depends only on, let's say, the modulus of x. So the rotational symmetry will be there, but the translational symmetry will be broken, of course.
It is mentioned on Wikipedia that this vector, which Azim is referring to, is already a constant of motion. But it is nothing. It is really also it is really in classical and quantum mechanics. No, there's nothing written about whether it correspond to
some symmetry or
not.
Yes, it does.
Does?
Yeah. Four-dimensional rotation.
I think there was a SO4, if I remember. This was a long time back when I was studying quantum mechanics. Yeah. There's an SO4 symmetry, I think. Yeah. Okay. Now let's go to the first non-trivial examples of the non-Euclidean group. So the idea will be to study the, we already discussed that, but let's do it a bit more systematically. SU2, so we'll start with SU2 and then move to SO3. SU2, so SU2, remember, we already, this was the discussion we had. We said is a set of, is a 2 cross 2 matrices, 2 cross 2 unitary matrices with determinant equal to +1, the determinant equal to 1. This was the definition of SU2. And we already checked last time, I think one of the times before that, this formed a group, right? Okay. So let's say, so the most general, I think I already mentioned this, but let's go through the proof actually. So we have, let's say the most general 2 by 2 matrix will be, these are complex matrices, right? Unitary matrices, they are complex. So these are 4 complex parameters are here, right? And they have to satisfy unitarity condition. So unitarity condition means this times the dagger of that should be equal to identity. Right? So dagger is simply Z1 bar, Z3 bar, Z2 bar, and Z4 bar. Correct? I mean, the bar meaning complex conjugation. Okay. So you have to take the adjoint, the dagger is the transpose and star and the complex conjugation together. So as that, that's equal to 1. So 1, 0, 0, 1. And then from this you get 3 equations, right? So one equation is Z1 mod square plus Z3 mod square equal to 1. And similarly Z2 mod square plus Z4 mod square equal to 1. And then there will be this equation, Z1 bar, Z2 plus Z3 bar, Z4 equal to 0, right? This equation is just a complex conjugate of that. So it's not a new equation, the same equation. Okay. And then, so we want to find the solutions of these equations. And apart from that, we have also determinant condition. So what is the determinant condition? That condition is Z1, Z4, minus Z2, Z3 equal to 1. Right? So these are the equations. These two are obviously real equations. This is one complex equation, and that's also one complex equation to begin with, it's a complex equation. Okay. So how do you first find the solution? So the idea is to, we can try various things. For example, let's say I take this equation and multiply by Z4 bar. You can do that, or you could do something Z2 bar or something. So multiply this equation, multiply by Z4 bar. So what am I going to get? I will get Z4 bar, Z1 bar, Z2 plus Z3 bar, Z4 bar equal to 0, right? Because right hand side is 0. So on the other hand, now I can use this equation. This is Z4 bar. So that's equal to 1 minus Z2 bar. So here you see you find Z4 bar. So this quantity becomes Z4 bar, Z1 bar, Z2 plus Z3 bar times 1 minus Z2 bar. That's equal to 0. Now if you look at this term together with that and there is a common factor which is Z2, right? So this part I can write, these two terms together I can write as Z2 and is that correct? Z2 and then Z4 bar, Z1 bar minus Z3 bar and Z2 bar. Correct? And of course I have this first term is there, plus Z3 bar equal to 0. So this equation is just that. On the other hand, this equation is nothing else but the complex conjugate of that equation. Okay? So this is therefore 1. So you get the conclusion Z2 is equal to, or Z3 equal to minus Z2 bar. Okay? So therefore we already found out that this object is nothing else but minus Z2 bar. Now in the same procedure you can again start and finally obtain the Z4 equal to Z1 bar. You have to probably start with something else, maybe multiply this by Z2 bar and then again go through these manipulations, and you can conclude that this means, actually maybe already we can see Z3. In fact, we can already see from here, right? If Z3, we already concluded Z3 is minus Z2 bar. So I just substitute that here. Okay. So bar of bar is Z2 again, so it's minus Z2. Z2 comes out as a common factor, and then you get Z1 bar plus minus Z3 bar. But that's not completely good because, I mean, it could be the Z2 bar is 0, right? But in the case where Z2 bar is not 0, then when this, in that case it will be purely diagonal. Anyway, I mean, you can go through exactly the similar type. You see, in this procedure, the point was that nowhere there was an issue of something could be 0 or not 0, right? In these steps. Because anyway, if something is 0, this should be 0 anyway. Then nothing happens. But you see, what I'm trying to say is that if I just substitute that here from this equation, I will find Z1 bar, Z2 minus Z2, Z4 equal to 0, right? So I can take out Z2 as a common factor, and I'll get Z1 bar minus Z4 equal to 0. Okay. But this does not imply necessarily that is equal to 0, right? Because it could be the Z2 is 0. Right? So you don't know whether, but for sure it says if Z2 is not 0, then Z1 equal to Z4 bar. Okay. But if you can go similarly, like here I multiply by Z4 bar, perhaps you should multiply by Z2 bar and go through the same procedure, and you should find that indeed this implied that this is equal to 0. Okay. So that's why you were saying that I mean, we already said this last time that the most general such matrix is Z1, Z2 minus Z2 bar and Z1 bar. You see, Z4 is Z1 bar. Okay. So this is together with one more condition. This is not the whole thing. I have the determinant condition, which makes it Z1 mod square plus Z2 mod square, or determinant condition, or that condition is well, okay, because Z3 is the same as minus Z2 bar, so the same, equal to 1. So the most general SU2 matrix is parameterized like this. In terms of two complex numbers, Z1 and Z2, subject to this condition. And as we said, this is nothing else. If I write Z1 is x1 plus ix2 mod square, and Z3 is a complex number, I can always write like that, two real numbers. And Z2
surface of a ball in 4 dimensions.
Huh?
The surface of a ball in 4 dimensions.
3, yeah, S3 exactly. So x3 plus ix4 square. That's equal to 1. But this is nothing else but x1 square plus x2 square plus x3 square plus x4 square equal to 1. So this is a 3-dimensional sphere.
4 dimensional.
No, I mean the surface is 3-dimensional. I mean that's a terminology. So for example, when we say, so the terminology is something like this. Sn, this is the n-dimensional sphere, is written in an n plus 1 dimensional Euclidean space. So you write x1 square plus x2 square plus all the way up to xn plus 1 square equal to 1. So this will be the equation describing Sn. So one variable higher. So it is embedded in a 1-dimensional higher, but the surface itself is, yeah. So this will be S3 in that language. Our usual sphere is S2. It's a 2-dimensional. The surface is 2-dimensional. The usual sphere. So this is S3. Okay. Now let's look at since we are talking about the infinitesimal generators, let's try to construct the infinitesimal generators. So this is three parameters, right? We have yeah, exactly, it's three-dimensional. S3 is three-dimensional. We have four real parameters, of which there is one equation, so one is fixed. So there are three parameters left over. And let's look at the identity. What is the identity? Well, identity is nothing else but taking Z1 equal to Z1 bar equal to 1 and Z2 equal to 0, right? So this, in this language, it corresponds to X1 equal to 1 and everything else 0, right? So identity corresponds to is Z1 equal to 1 and Z2 equal to 0, which is in the language of real variables, it means X1 equal to 1 and X2, X3 and X4 equal to 0. Okay, so what we do, we start from X1 equal to 1 and start making changes, I mean small deformations. Okay. Now, so if I make small deformations, so what's going to happen? Let's look at the, so let's take x1, so everything, let's make x1 goes to x1 plus delta x1, and similarly xi goes to xi plus delta xi. Okay. Let's, and then plug it in these equations. In this equation, okay, to see what is the condition. So I have four parameters. I started this my identity 1 0 0 0. So the identity is 1 0 in these coordinates 1 0 0 0, right? And now I look, I consider a small change. So I make change 1 plus delta x1, delta x2, delta x3, and delta x4. Okay. Small change. And I will be looking at the linear order in the small change. Now, of course, I cannot change all these four independently because our space is actually three-dimensional, right? So there must be some condition. And that condition is because we still have to satisfy this condition, right? It's not that arbitrary Z1, Z2 is allowed. This condition has to be satisfied. Okay. So if I plug that in here, in that equation, which is this equation, x1 squared plus x2 squared plus x3 squared plus x4 squared, you find, so the equation sum over xi squared gives you, of course, 1 to the 0th order, right? But then to the first order, you find, because when I take the square of that, you will get 2 times delta x1, right? And then delta x1 squared, but that's second order. Okay. So from here, you will get delta x2 squared already, second order, second order, second order, correct? So then plus order, second order delta square, delta xi square, or delta xi, delta xj could be, whatever. Quadratic in the small change. But we are ignoring the quadratic terms. Huh? So you see that to the linear order, we are finding that delta x1 has to be 0. Okay. So delta x1 has to be 0. That's what it tells you. So this implies that delta x1 is equal to 0. So the only changes are here. So this has to be 0, but here you can arbitrarily change to the first order. So let's see how the matrix looks like then. So if I write down the matrix, this is the matrix. So you find that here you have x1, delta x1 is 0, but x2, which is I times, this is I times x2, that is I delta x2. Okay. That is from here. Here I have z1 bar, so it will be 1 minus I delta x2. Right? And z2 is, we said, delta x3 plus I delta x4. And this is minus z2 bar, so minus delta x3 minus, so bar, so plus I delta x4. Okay. So this is to the first order, when you deform, when you make a small change in this thing, from the identity you find that. So which is the same as the identity itself, plus a first order thing, which is I. Let me put here I. Let me take out I. So delta x2 minus delta x2, and here you get delta x4 minus I delta x3, and here you get delta x4 plus I delta x3. Okay. So that's the first order. Plus up to second order, up to order delta square. Up to order delta square. So in fact, I mean, the reason for this is not surprising.
I think there is a typo here because we should the 3 or 4 are squared together.
Sorry, repeat that again.
The 3, the indices 3 and 4, they should be inverted.
Should be inverted, is it?
Yeah. Just a typo. It's written in the step before it is right. In the entry 1, 2. Yes. It's 3, 4. That's correct.
No, because I took out an I.
Okay.
I took out because I was here already, so I just
Okay.
took out I for convenience. Yeah. That's why you get minus I times I is plus. So that's that is that. Yeah? But here is my I times this is plus I. So that's minus. So that is the minus delta x3. No, that's just for convenience, nothing. Yeah. But before this, I mean, you see the meaning of this. Why this became 0? That is because you see. It's like, I mean, the identity which corresponded to this 1, 0, 0, 0. Think of it as kind of, I mean, on a sphere, let's say some north pole. Then when I go tangentially along the sphere, I will not increase the value of that or change the value of that, right, to the first order. To the second order you will change. But in the first order you will just go, tangential to the sphere. That is those 3 directions, x2, x3, x4. Right? So the generators are really tangent space. Okay? They are generating the tangent space of the group at the identity. I mean, that was the reason for delta x1 equal to 0 condition. Okay. Now, so let's see this object. So it's a 3 parameters, independent delta x2, delta x3, delta x4. They're 3-dimensional. SU2 is 3-dimensional. So the number of infinitesimal generators is also 3-dimensional. Right? That's indeed what you will get if I make this. If I use the definition that we were having. So we have this G is the group element as a function of these parameters delta x2, delta x3, delta x4. I mean, delta is just indicating that this is true only to the first order. We cannot trust that to higher orders, right? But to first order we can trust it. But that's all we need to get the generators, because you take the first derivative and then set the parameters 0, right? So first order is enough for the generators. So the various generators will be delta G by delta x2, and then set everything to 0, delta G by delta x3, everything to 0, delta G by delta x4, everything to 0, right? So that will give me 3 independent generators.
Pauli matrices?
Huh?
Pauli matrices.
Exactly. That's the point. That's why I wrote like that. Actually, I times the parameters, right? So if I take delta x2 variation, so you see that delta x2 appears here, not there. You have 1 here and minus 1 here. So this guy gives me, there's an I in front everywhere. 1, 0, 0, minus 1. X3 gives me I, sigma t, 0 minus I, 0. And x4 variation gives me I, 0, 1, 0. These are the 3 Pauli matrices. So this guy is I times sigma 3. And this is I times sigma 2. And this is I times sigma 1. So, and an arbitrary first order thing can be linear combination of any one of them. So that's what we said, is delta x2 times that, delta x3 times that, delta x4 times that. So it defines a vector space, a 3-dimensional vector space. Now notice that in the way we have defined These guys are anti-hermitian because this I factor. Okay, that is to be expected because G is unitary, right? So if I write G, after all, what we are writing is G is equal to 1 plus some X, let's say, to first order. X is some matrix. But now if I take G dagger, that will be one dagger of 1 is 1. But here you will get X dagger. Okay. And then if I take the product of these two, after all, G dagger, G is supposed to be equal to 1. That is unitary, right? So 1 plus X dagger times 1 plus X, just open it up, you find here 1 meaning it's a matrix, the 2 by 2 matrix, identity matrix. Identity plus X dagger plus X plus the second order. But second order we are not trusting anyway. Order X dagger X. We don't care about it because anyway this is supposed to be true only to the first order. So we don't care about that, but we do care about that. So this has to be 0. But that tells me the X dagger is minus X, which means X is anti-hermitian. Okay. Now this is just a matter of convention. Actually, even during this next lectures, I'll keep changing the convention back and forth. Usually, people prefer to write it as Hermitian matrices. Okay, so in that case, you don't expand like that. You put already an I here. Okay, so it's a matter of your choice. If you do that, then you have I here. Sorry, this will be minus here because when I take the dagger, I have minus here. So this will be minus, and now you see you'll get minus plus. So unitarity means X dagger equal to X, so it's Hermitian. But that's a matter of convention, whether you absorb I inside you remove the I or if you keep I. It's a matter of.
Is this the only reason we keep seeing all these I in front of generators? Because easily we do the same tricks without introducing any I. For example, when we are Taylor expanding the elements, we don't see any I, but to make them Hermitian, to make the generators Hermitian.
Yeah, that's right. I mean, so now you would say that you will expand. So what does it mean to write like? So this, of course, means it is if I make an expansion, so I mean, so it's like here what we said is delta x2 times sigma I sigma 3, and so on, right? We wrote like that. So when I take the variations in delta x2, then I get, of course, I sigma 3. On the other hand, in the physics literature, usually, you don't expand like that. You expand like this. I mean, I delta x2 times sigma 3. No? So, and whatever the coefficient of sigma 3 is your parameter.
So this is just a convention. For example,
It's a convention.
For U1, the generator could be I, but is anti-hermitian. So
Yeah,
if
exactly.
we use that convention, the generator would 1.
That's okay. The mathematicians like to, mathematics literature, they will just write like that. I mean, no, not I, not put I. In that case, their axis would be anti-hermitian. But physicists put an I there. Okay? Because we like to deal with the Hermitian matrices. But it's a matter of, there's no difference between the two. Okay, so this is the generator. But now here you see that this group is non-abelian, right? So there is another very interesting structure. So of course, as we see, the generators form a vector space, right? Because it's a tangent space around them. It's a vector space. There's a notion of adding and subtracting, multiplying by numbers. Huh? All that is there. Okay? So that is fine. So this is the basis, sigma 2 or either I sigma 3 or sigma 3, depending on your preference. That is the basis. And you can multiply by any numbers and add them up. So it's a vector space. But there is a much more important structure here. And that you have seen probably already in your university. I mean, when you are studying. These are called Pauli matrices, right? Pauli matrices. And they satisfy a very important property that sigma I, sigma j commutator is I, 2i, I think, epsilon ij k sigma. A commutator. So this is like an extra structure we have here. Okay. So it is not just any vector space. It's a vector space which comes with a bracket structure. So it's an anti-commutator. It's an anti-symmetric structure that exists. So it is telling you that I can associate, give me a pair of elements of in the algebra, in this vector space. I have a rule, I can define a consistent rule which is anti-symmetric in such a way that this is mapped, a pair is mapped to a third element. Okay? So this is a kind of, this is called the Lie algebra structure, or Lie bracket structure. This satisfies Jacobi identity. Okay, that is obvious because matrix multiplication. This is matrix multiplication. Yeah.
You said that the tangent space is spanned by Pauli matrices, 3 matrices.
Yeah.
But normally we don't introduce multiplication between vectors.
Yeah, that's the point.
Here it is multiplication.
Yeah.
But normally, for example, in R to the n, do we have an analog multiplication between vectors? Is it like inner product for tangent?
That's the point. I mean, when you take the inner product, it's mapped to numbers.
A number.
Yeah.
Here
it is mapped to the vector space itself.
The 2 elements mapped to one element.
Yeah.
So is it just a vector space in that case?
No, that's what I think. It comes with an extra structure.
No, not the brackets, the multiplication part. This is also an extra.
The multiplication is not defined here. Right? I mean, the multiplication, if I don't have the bracket, if I don't take the commutator, it doesn't make.
But when I see the commutator, I think sigma I times sigma j minus sigma.
True. That is fine. I mean, that is since we have a matrix.
Yes.
But in a more abstract way, there is no meaning of multiplication.
Yes, because they are vectors.
Yeah, precisely. Yeah. So here we are talking about what is it is a Lie bracket structure. It's really the bracket structure. Multiplication itself is not well defined. Huh?
So we can just define it like this.
Yeah, precisely. Without. I mean, this we can evaluate explicitly because we have matrix realization.
Fortunately, we can do, but we didn't.
That's right. But what is guaranteed is that even in completely abstract way. See here SU2 we define it in terms of matrices, right? But suppose you define some abstractly the group, Lie group. I will continue with some continuous parameters. You can define this quantity which, so there is no meaning of saying sigma 1 times sigma 2. But what has a meaning is the commutator. Okay. Yeah, exactly. So it's a map. So if V is the Lie algebra, if V is the vector space here. So this is a map, V cross V to V, which is antisymmetric. Because this commutator is clearly antisymmetric. Antisymmetric. It satisfies the Jacobi identity. So these are the two main points here. So what is Jacobi identity? If I take some x and y of the vector space, so concretely, what is x? X is some, I can expand in terms of this basis. So x will be some xi times sigma I for some xi. Right? Similarly, y would be some yi times sigma I, some lower I. Right? So this will, and suppose I have another guy z, then the Jacobi identity is satisfied, which means the sum of this, when you cyclically go around, the sum is 0. So which means z, x, y plus the again cyclically go y, x, y, z, x equal to 0. So this is what is called the Jacobi identity. This is automatically true for matrices. Matrix multiplications always satisfy this condition. But this is in a more abstract setting, when you don't think of the group as given by some matrices that you can, so you impose it by hand. And we'll see somehow the origins of these objects. Of course, note. So what is this? All the Pauli matrices have the property that these traces of this Pauli matrix is 0, right? But that was exactly the reason for which you remember we had this, the identity was 1, 0, 0, 0 in the notation of x1, x2, x3, x4, right? And the fluctuations, the small changes this was fixed. And you had delta x2, delta x3, delta x4, right? But the reason why, but all of these things corresponded to, did I erase that? No, I didn't erase. You see, delta x2 is multiplying sigma 3 and sigma 2 and sigma 1 and sigma 2. They're all traces. The reason why is because delta x1 is 0. If delta x1 was not 0, that would come with the delta x1 plus delta x1, right? Or I times, okay. That trace will not be 0. So precisely for that reason, because what we are saying, the trace has to be 0. And the tracelessness condition is coming from the determinant equal to 1 condition. Okay? That's the reason. And the way to see this, let me just, again, this probably you have seen it in one way or the other, but let me just say it. So whatever this matrix M is, M belonging to SU2, we have the condition that determinant of M equal to 1. Okay? That's the condition. But this I can write, there's another way of writing it is, this is the same as exponential of trace of log M. Okay. This I can write formally. Okay, you don't ask me what you mean by log M. But
Can just expand it as value series?
Yeah, true. Yeah, you can do it.
Always problems with conversions.
Yeah. But since we are interested in near the identity, we are interested in M close to identity. Okay. It makes perfect sense because then you write M is equal to identity plus some X, no? And then you can do a log expansion. And we are interested in the first order.
Okay.
No, so that will be perfectly okay. But the easiest way to see this is, let's suppose I can find the eigenvalues of M. Okay. So let's suppose lambda I are the eigenvalues. I going from, what in this case is 2 by 2 matrix, so it's only 2. But in general, now let's discuss completely generally, some n by n matrix. So we have 1, 2 up to n, no? Some eigenvalues in this matrix. Then the determinant by definition is a product. 1 to n, lambda I. Right? But this I can write as exponential of sum over log lambda I. Okay. But log lambda I will be the eigenvalues of log m. Right? If I can diagonalize m, m is just a diagonal matrix, and log is simply that. So this is log m. So it's a trace of log m. Or another way to say is that log m is some matrix whose eigenvalues are log lambda I. But for us it's not a problem because we are always near identity and to the first order. So this is no problem. But this trick will be used many times. When you go through the quantum field theory in the particular next semester, this trick will be used not just for n finite, but n equal to infinity. Because this will be, then you will be dealing with infinite by infinite matrix. But this kind of tricks will be used. Okay. So going back to this our SU2, this question. So it's a 2 by 2. So we said determinant of n is the same as exponential of trace of log n. Okay. But then we want to look at n equal to identity plus some small first order in x, right? So if I substitute that there, then right hand side becomes exponential of trace log of 1 plus x, but log of 1 plus x is x to the first order, right? Log of 1 plus x. 1 is a matrix now, of course. This is the n by n matrix. But in general, say suppose it's a number 1 plus x. It starts with the x, then minus x squared by 2. If I make a Laurent expansion, Taylor expansion, I'll get something like that. No? So, but we are not interested. We don't want higher terms. So the first term is simply that. And again, I can expand because I'm looking at the first order in x. So I can write this as 1 plus trace x, right, to the first order. This is all I should put it like this sign. This sign means approximately. This all is true only first order. So this guy is approximately equal to that, the first order. But on the other hand, we have the condition that the determinant of m is 1 for SU2. So we are saying 1, so that means, I mean, it should not change. Whatever I'm looking at small change, it should not change the determinant condition. But that means trace of x must be 0. That's a way to understand that for SU2, or in general SUN, because SUNs are all n by n unitary matrices with determinant equal to 1. Whenever you have determinant equal to 1 condition, that means the generators will be traceless. That's the important part. Okay. Instead of SU2, suppose you had done U2. Okay. In U2, there will be no such condition. Okay. In that case, the generators will not only be Pauli matrices, but also identity matrix. Okay. So it's a 4-dimensional. U2 is 4-dimensional. So U2 will be generated by Pauli matrices and identity. Identity is the one which has trace not equal to 0, right? So that will be 4-dimensional. Now this is this algebra will play a very important role. I mean this Lie algebra. So by the way, because of this, I mean because it's not just just any arbitrary vector space. It's a vector space which carries this bracket structure. Okay. In general, the vector space will not carry such a structure. Right? But what we are seeing is that the space of generators that come from continuous groups, they have this property already. Okay. And next time I'll go through this in more detail. But here we see by actual construction, by actually just working out this, that there is this algebra structure. So that's why these are called Lie algebras. So Lie algebra is a vector space together with a map, an antisymmetric map which satisfies the Jacobi identity. It's a linear map. Yeah, I think we'll continue that next time. So then after this now I'll go to the SO3 and we'll show how precise relation between SO2 and SO3. Okay. That is a 2-to-1 map. So we will go through that. All right, so any questions? A quick question you have? Okay, otherwise we'll see you tomorrow. This, I mean, I will keep forgetting it.